Next, I'd like to talk about a couple of the properties of the wave function. First off, some plots, and then the 0-point energy. So what I have here are graphs of psi n. So n equals 1, 2, 3, 4. I've roughly tried to put these in order of energy, although this looks a little bit too even here. Remember, it goes up as n squared. So notice, this is a sine function here for n equals 1, for n equals 2. These are all sine functions. But one of the things we can see is we have a node here. For n equals 3, we have 2 nodes. For n equals 4, we have 3 nodes. These are the wave functions. What does this mean for the wave function squared? Remember, the wave function squared is the probability of finding the particle in space. If I want to find the probability of finding the particle in, say, from 0 to a over 3, what I do is I take the integral of psi squared over this region. And what I see for this is I see a single maximum in the middle of the graph for n equals 1. For n equals 2, because I changed sign here, I have a node. What does this mean? I will never see the particle at this point. I see the particle here, I see the particle here. I never see it in the middle. For n equals 3, the same thing, except now I have nodes. I have 2 nodes here and here. Again, I will never observe the particle at those regions. It's a standing wave. The particle is a standing wave. Excuse me. Finally, n equals 4, the same thing, except I've got one more. I mentioned the 0-point energy. So 0-point energy is the energy that the system does not have 0 energy at its lowest energy point. In fact, remember, energy is equal to m squared h squared over 8ma squared. For n equals 1, the lowest energy state, the energy is h squared over 8ma squared. How can this be? Well, one statement of the uncertainty principle is that the uncertainty in x times the uncertainty in the momentum in x must be greater than or equal to h bar over 2. That's a mathematical statement of the uncertainty principle. What does that give me? Well, what that tells me is, imagine if my particle had 0 kinetic energy. If it had 0 energy, I would know exactly what its momentum was. Its momentum would be 0. If I knew exactly what its momentum was, the uncertainty in its momentum would be 0. The uncertainty in its position would be infinite. Similarly, if I knew exactly where the particle is, I have no knowledge of its momentum. So I can't have a particle in this situation with 0 energy, because that would violate the uncertainty